So we have learned that the Fermi level is constant in equilibrium. So now the question is, what happens to the Fermi level when it is in non-equilibrium? So what I mean is, when you apply a voltage or when you shine light on a semiconductor, what happens to this Fermi level? So in short, the Fermi level splits into two distinct levels, which we call as quasi-Fermi levels. So in this video, I'll be explaining how the Fermi level splits into quasi-Fermi levels and what is the physical significance of these quasi-Fermi levels. So firstly, let's quickly recap what equilibrium is. So it means that the net charge transfer is zero. So this is equivalent to telling the current is zero. And the one more condition is that net energy transfer is zero, which implies that the applied voltage or light or heat on a semiconductor is zero. And we also know one more thing, that the Fermi level is constant in equilibrium. So suppose I have a n-type semiconductor. So a single Fermi level is actually enough to represent both the electron and hole concentration when this material is in equilibrium. So now let's see what happens to this n-type silicon when it is exposed to non-equilibrium conditions. So what we will do is we'll take this n-type silicon and at one of its end we'll shine light on it, and let's say the doping concentration is 10 power 16 per centimeter cube and the intrinsic carrier concentration is 10 power 10 per centimeter cube. And let's say because of the light, the rate of electron and hole pair generation is about 10 power 16 per centimeter cube. That is, delta n is 10 power 16 per centimeter cube. Okay, now let's see how the energy band diagram for this device looks like. So far away from the source of light, we see that we just have a single Fermi level, and this is actually enough to define both electron and hole concentration. So the electron concentration here is actually 10 power 16 per centimeter cube, and the hole concentration is 10 power 4 per centimeter cube, and this is actually obtained by Np is equal to Ni square. This is what is called as law of mass action. So now let's see what happens to the Fermi level in the region where we are shining light on the semiconductor. So the concentration of electrons, that is, this is the new concentration of electrons, is equal to delta n plus n. So n is the old concentration that was there before, and delta n is due to the generation process because of light, and this is equal to 2 into 10 power 16 per centimeter cube. Similarly, the concentration of holes is equal to delta n plus p, and this is also approximately equal to 10 power 16 per centimeter cube. Now clearly we can see a problem here. Just having one Fermi level, we won't be able to tell what is the electron and hole concentration, because we see that both the electron and hole concentrations have changed. Especially we can see that the hole concentration has changed significantly. So what happens is the Fermi level actually splits. So we see that for electrons we have a separate Fermi level called EFN. Similarly, for holes we have a separate Fermi level that is represented by EFP. Now these two Fermi levels are used to represent the holes and electron concentration in non-equilibrium conditions. So now let's try to understand what is the physical significance of this quasi-Fermi levels. So for example, in a solar cell, the voltage that is generated is directly proportional to the separation between EFN and EFP. This actually directly translates to the efficiency of the solar cell. So what it tells us how much is the voltage that is generated when there is sunlight on the semiconductor. Similarly, in the case of transistors, the gain is actually directly proportional to the separation of EFN and EFP. So taking an example of a BJT, so this separation actually tells what is the efficiency of current that is being injected from the emitter to the base. So this directly implies what is the gain of the bipolar. So this is the physical significance of quasi-Fermi level, and as we can see, the quasi-Fermi levels are very important in order to analyze semiconductors in non-equilibrium conditions. So that's the end of this video, and see you in the next one. And thanks for watching.